A sketch of this setup is shown here. A support holds the spring, then a mass is placed on the spring. The weight of the mass acts downward while the force from the spring acts upward. When displaced from equilibrium, the spring will oscillate and transfer energy. The way the energy is transferred will be measured using initial and final positions of the spring.
For this lab, we used a meter stick, several masses, and a motion sensor, which we used to generate position graphs on SparkView. For this lab, we put several masses at the end of a spring and stretched the spring away from its equilibrium position to study its oscillations. Here we see the kinetic energy of the mass become zero because the spring is expanding back to its equilibrium position, and here we see the kinetic energy of the mass become zero again as the spring tries to compress back to its equilibrium position. Here is how we recorded data in the lab. One of the biggest roadblocks we hit was keeping the masses attached to the end of the spring.
Okay, is it at 40 centimeters?
Yeah. Oh my gosh! In order to calculate the change in energy over half the period of the spring, we first calculated the spring constant, which you can see our calculation values right here. And we did find the average of 4 different spring constants that were calculated with 4 different mass values. And we applied conservation of energy, you can see the equation right here, by finding the change in the height of the spring and setting the change in gravitational potential energy equal to the change in spring potential energy and finding those spring constants. And again, we averaged the 4 to obtain the spring constant we were going to use. From here we could begin the 4 different trials that we did with 4 different masses. You can see those masses right there. And then to do the actual experiment, the mass was pulled down so the spring was out of equilibrium. You could see with the mass added, there was no movement at those values that I highlighted right next to, and you could see that each of these values that we initially pulled it down to is below the value of that no movement. And then that position was recorded by SparkView. That's how we found those positions. And then the highest point of the oscillation, the final position, was also recorded by SparkView. These points are of interest because the kinetic energy at each of those points is equal to 0 because there's no motion. At the top and the bottom of the oscillation, there is no motion because velocity is instantaneously equal to 0. And this simplifies our calculation later because if we add up all of the energies before or at the bottom and at the top of the oscillation, we can find that if energy is conserved and not having kinetic energy is really useful. We calculated the gravitational potential energy at both the bottom and the top of the oscillation by the equation U sub g is equal to mgh. You can see that right there. And then we calculated the spring potential energy at these same points by the equation U sub s is equal to 1/2 kx squared, where x is equal to the equilibrium height, which is equal to 0.7333 at each of the spring positions. That's the height that the completely unstretched spring, the relaxed spring, is at. And we subtracted the height of whatever point we were using. So for example, the initial spring potential energy for the 4.05 kilogram mass was calculated with 0.7333 minus 0.2672, and that was the value of x for that one. From there, we calculated the total initial and final energy of the mass and spring system, and you can see those values for each of them here and here. That was really simple. Adding initial energy is just the initial gravitational potential, and the initial spring energy, and final energy is using the same thing but using final energies. And then we found the change in energy by subtracting final energy minus initial energy. And then our final calculation was to average those values, and we average the differences to find an average value for the delta U.
In the lab, the spring constant was found first. Then more trials were done to try and show energy in a conservative system is constant. In an ideal world, this would happen. However, this isn't an ideal world. In every trial, there was a loss in energy. This can be attributed to the errors in the lab. First of all, friction or air resistance could cause a loss in energy. Also, when the spring would oscillate up and down, wouldn't go straight up and down, sometimes it would go side to side. Next, the spring could have stretched a little during experimentation, which can change data or the spring constant. Finally, there could be human error. The meter stick readings might be a little off, which would change or make the energies a little off too. Humans also can't make everything completely constant. This would throw the data off as well. All in all, initial energy should equal final energy in an ideal world, but this did not happen.